Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin. Rewrite the following as one iterated integral by changing the order of integration. So we have two integrals here, and what do we want? Well, we want one integral to rule them all, one integral to find them, one integral to bring them all, and in the light of multivariable calculus, bind them. All right, so how do we begin? Well, notice we're not actually doing any integration, so it's all about describing what's going on. So let's think about what's happening here. So remember that things connect. So the inner layer connects with the inner, outer connects with the outer. So let's start by describing our current regions. So here, the outer part tells us negative 14 is less than or equal to y, less than or equal to 2. We know it's y, and then we say negative 14 to 2. Then the next layer says negative square root 11 minus y, less than or equal to x, less than or equal to y plus 4 over 2. Again, we know it's x, and then, from the bottom to the top. All right, same thing's going on over here. 2 less than or equal to y, less than or equal to 11, and we have 2 less than or equal to x, misread that. Negative square root 11 minus y, less than or equal to x, less than or equal to square root 11 minus y. All right, now there's a different sign here, so they're not the same thing. So let's see if we can get some sketching going on. And we want to sketch the curves. So right now, when we're thinking about curves, it's the inner layer that's the curves. The outer layer is numbers. So we have what looks like essentially a few functions. Well, let's see, we have x equals minus square root 11 minus y. And that's not so clear what that might look like, but we're pretty commonly, we're familiar with y equals stuff. So let's solve for y. If you square both sides, we get x squared equals 11 minus y, or y equals 11 minus x squared. Ooh, that's probably going to be an upside down parabola, because it's going to be an upside down parabola. All right, now the other curve. X equals y plus 4 over 2. Again, we can solve for y double both sides, subtract 4. Y equals 2x minus 4. Now here, you'll see we still have the same bottom curve. For the top curve, if you go through the same process, you're going to get the same curve. It's almost like it's two sides to one curve. And that's because that's what's happening. All right, so let's see. Let's try to get a sketch here. And so we know our curves. All right, actually we'll probably need to go down a bit. And all right, so we have, first off, 11 minus x squared. So we're going to come up here to 11, and then we're a parabola going down. So parabola going down. There's our parabola. Y equals 11 minus x squared. And the reason I'm labeling it as y equals 11 minus x squared is I'm anticipating that we're going to be switching in terms of our order of integration, because it tells us to. So I want to change from x as a function of y to y as a function of x. So the old bounds, when we integrated dx dy, well, the square root 11 minus y, that's the right-hand side, and then the left-hand side is negative square root 11 minus y. But again, we want to switch to y equals. Okay, now this other curve, y equals 2x minus 4, well, you come down here to negative 4, and then you're going to go at an angle, and something like that. And okay, it's not perfect, but that's okay. We just need to get an idea of what's going on. Now, we really are strongly interested in intersection points. Okay, so, and we're interested in that point as well, in some sense. See, that 11, notice, that matches with here. Now, we suspect that that tells us that this should be y equals 2. Okay, well, suppose that were the case, right? Because that makes sense. That's a sort of a change. So if we put in y equals 2, let's see what we'd get. And, well, we'd get square root of 11 minus 2, which says that this is at square root of 9, which is 3. And now if we put 2 in here, sorry, a dramatic pause. So when I put 2, I put y equals 2. So here, if y equals 2, because remember this is the curve x equals y plus 4 over 2. So I was trying to put x equals 2. No, it's y equals 2. So 2 plus 4 over 2 is 3. So actually that's right. They do intersect here. Not a coincidence. Well, how about this one? Where is that at? Well, we suspect this should be y equals minus 14. Well, let's find out what happens. When we plug it into this curve, we'll get 11 minus 14. That's 11 plus 14, 25. And square root of 25 is 5. So this seems to be negative 5. Now, is that also true here? So negative 14 plus 4 is negative 10. Negative 10 divided by 2 is negative 5. All right, good. So this is at negative 5. All right. Now, you could have also done the following. Maybe you could have said, well, set 11 minus x squared equals 2x minus 4. And then you could say, oh, we'll move everything to one side. And then you'll get x squared plus 2x minus 15 equals 0. And then you'd be like, And you're like, oh, that can factor as x plus 5 times x minus 3 equals 0, which gets you the intersection points of negative 5 and positive 3. All right, so here we go. Let's recap what's going on, and then let's write down the answer. So currently, we have two integrals. One says go from negative 14 to 2, and go from negative square root of 11 minus y over to this y plus 4 over 2. So it's saying do this part here. And I'm moving this deliberately, so we're going horizontal slicing. And then we say, okay, we hit our second integral, and that one's going from y equals 2 to y equals 11, and again, we're going from left to right. So it's doing that integral. Now we say, okay, we want our new integral. We're changing the order of integration, so we're changing the way we slice. So now instead of horizontal, we're going to do vertical slicing. And the nice thing is, if you look, as you move from left to right, it's always the same curve on top and bottom. That's why we only need one integral, because we don't have a change in the curves like we do as we slice horizontally. So what's our one integral? Well, it's going to be f of xy dy dx. Now this we could have written down before we even started. Say, okay, where does x go from? From negative 5 to positive 3. Where does y go from? From this line, 2x minus 4, up to that line, or in this case, parabola, 11 minus x squared. And that's it. All right, so good. Our plan, and we're going to do this a few times. Use the existing integral to grab the description, which, in other words, these are describing your region. Plot the curves, and then say, okay, what's going on? Label our curves with our functions, and it's probably helpful to label it both x as a function of y as a function of x. And now think, look, we're going from slicing one way to slicing another way. And there we go. Life is good. A nice start, right? Yeah. evaluate the integral from 0 to pi over 4, integral from x to pi over 4, secant squared of y over y dy dx. Now, our initial reaction is like, oh, well, why don't we just integrate this one layer at a time? And then we look at the function and we say, oh, well, that's why, because that's hopeless. There's no way we can integrate that. And so we say, okay, so we're not going to do that. So what can we do? Well, the problem is we can't integrate this with respect to y. However, we could integrate this with respect to x. Because if you look, you say, oh, there's no x terms here. So when we integrate with respect to x, it's essentially a constant. And that's one of our favorite integrals. So we have an idea. Let's first change the order of integration, and then let's do the integral. All right, so we need to understand, wait, what's our region? So we're going to look at our bounds. So we, of course, do our matching. And we say, well, currently, x is going between 0 and pi over 4. Then y is going from x to, again, pi over 4. So if we sketch, well, we have two curves that are important. We have y equals x and y equals pi over 4. So y equals x, let me switch colors here. That's a straight line. Oh yeah, we like lines. And it's one of our favorite lines, actually. Here's our line y equals x. Now, that's y as a function of x, but we can also write it as x as a function of y. See that? Yeah. That's what, a college education does. It lets you say, oh, if y equals x, x equals y. Booyah. All right, now, our other curve will be y equals pi over 4. So let's sketch it here, pi over 4. And now we're saying go from x equals 0, and that's here, and we're going to go from y equals x up to pi over 4, and we're going to keep doing that up until this point, pi over 4, which, by no small coincidence, that's where the curve y equals x and y equals pi over 4 intersects. All right, now that's the current way to integrate. So we need to switch. How do we switch? Well, we're now going to go slice in the other direction. So we're slicing that way. So this will become integral, integral, same function, because we're not changing the function, we're changing the way we describe the region, which allows us to change the order in which we do the integration. Now, where does y go from? Well, it goes from 0 to pi over 4. Okay, well, that doesn't seem like a big change, but these are actually different. You look at this and say, oh, you didn't change anything, but actually we did. So I want to point this out. So just we get into the habit of things. And what's our change? Notice these are x bounds. X equals 0. X equals pi over 4. These are y bounds. So even when things might look the same to the casual observer, we know in our heart of hearts, there's actually a subtle thing that has changed. Now, what about our inner layer, where we're going from the axis? That corresponds to x equals 0. That's the axis. So 0 over to the line. And that corresponds to x equals y. All right. Good. Good. All right. Now, what comes next? Well, we just follow and do the rest of the problem. Okay, so we already mentioned that now, since we're integrating with respect to x, the secant squared y over y, it's a constant. So this becomes the outer layer, which we haven't done anything to. Secant squared y over y, our constant x. Evaluate x equals 0 to x equals y, because these are x bounds here. X equals 0 to x equals y. Just like over here, you're going to write y equals x. Y equals pi over 4. All right, and don't forget the dy, because notation matters. In multivariable calculus, it really is super important, because the order makes a big difference, right? Okay, so when you plug in x equals y, you get y. When you plug in 0, you get 0. And notice, when you plug in y, it cancels with that y. So this becomes integral from 0 to pi over 4 of secant squared y dy. Do we know the integral of secant squared? Tangent. What? It's like they wanted us to succeed. Okay, so tangent y from 0 to pi over 4. Tangent of pi over 4 is 1. Tangent of 0 is 0. So we end up with 1 minus 0 or 1. All right, good. So when faced with what looks like an impossible integral, think to yourself, can I change the order of integration and make some progress? And if you can, that's probably the way to go about solving it. So nice. Find the average value of the x-coordinates of the points in the region in the first quadrant lying in the disk of radius 2 pi centered at the origin. In other words, that's what EG stands for. Our region is r theta, points r and theta, where r goes between 0 and 2 pi, theta goes from 0 to pi over 2. Well, they didn't need to give us that, but that's okay. They're being generous. They're being nice. So we're in the first quadrant. So, okay. So here, the x-axis, that's theta equals 0. Theta equals pi over 2. And our region is a part of the disk, or a disk is just a fun way to say a filled-in circle. And we're going out to a kind of a curious radius, 2 pi. That's all right. We are okay with that. So we have our region, and I should shade it since it is a two-dimensional region. Now, given how it's a circle, polar coordinates makes a lot of sense. Also, they're trying to tell us do polar. Because see how they say r and theta? They're really trying to say polar, polar, polar. Could we do it nonpolar? Maybe. But I suspect that by doing it bipolar, it's reasonable. And nonpolar may or may not be reasonable, so let's just do it the way they suggest. Now, how do you find averages? Let's do a quick recall. So we'll do a Calc 1 recall and say, all right, how do we go about finding averages? Well, when we talk about the average value of a function, the way we would do it is we'd have this 1 over b minus a integral a to b of f of x dx. And you say, okay, well, wait, what's going on? Well, what you're doing is you're adding up the values. So remember, that's what integration does. You add up the values. Okay, that makes sense. If I want to find an average of something, I need to add things up. But then you have to divide. So we have this term, b minus a. Why are we dividing by b minus a? Where is that coming from? Well, picture-wise, what we have is we have our curve doing whatever curves do, and we have our point A and our point B, and we say, okay, so we're trying to find the average value of the function, and we say, well, what does b minus a correspond to in this picture? And when we look at it, we say, oh, you know, b minus a, that's how far apart a and b are. And another way to think about it is to say, oh, b minus a, this is the size of, I'll put size in quotes, of our region. Okay? So that's what's going on. B minus a is the size of our region. And you could also really express b minus a in another way. So it's saying add up a to b f of x dx, that's adding up the values, and then we're going to divide by add up just how many things we have. And so the way you do that is you integrate 1. And you can check, if you integrate 1, you get x. And then evaluate b to a, that's b minus a. So it's like, okay, cool. So, what's our plan? So our plan is we want to do this, same idea. We're going to find the average is, we're going to integrate over our region, the value x, divide by the integral over our region, the value 1. All right, so that's our average. Okay, now with that out of the way, we can say cool, 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 cool. So what do we do next? Well, there's one of these is actually going to be really quick. Notice we're integrating 1. What do you find when you integrate 1? Well, when you integrate 1, this is the same as the area. So the integral of 1 is area. Well, it's a quarter of a circle, so it's 1/4 of a circle, and so the area of a circle is pi, and then you have r squared. So 1/4, because it's 1/4 of a circle, pi r squared. Well, okay, 2 squared is 4, that cancels, so we have the denominator will be pi cubed. So we don't really have to do a lot of work for the denominator. Now, for the numerator, we've got to put some work in, but that's okay. We don't mind. We like putting some work in. And we say, okay, great. So let's set things up in polar. What do we have? Well, we have integral. We have to convert x into polar. Well, that's going to become r cosine theta. X equals r cosine theta, y equals r sine theta, and of course the famous x squared plus y squared equals r squared. All right, so we have our nice little facts, and now that's the x. The dA will be r dr d theta. So don't forget this r. That's very important, and it's very easy to forget. We know the bounds for theta. That's going from 0 to pi over 2. We know the bounds for r. It's going from 0 to 2 pi. So great. We're in good shape. Now, don't forget, all of that divide by pi cubed. Okay. Well, now pretty much the last thing to do is carry out the integral. And so we'll just be patient and work it through. So, okay, so there's a 1 over pi cubed. I'll write that in the front. Then we have integral 0 to pi over 2, integral 0 to 2 pi, and r is r squared, cosine theta, and then dr d theta. Now, we can do something fun, which is we can actually pull this into 2 integrals if we wanted to, if we were in the mood. I'll go ahead and just do it one layer at a time. So we have our 1 over pi cubed, integral 0 to pi over 2, integral of r squared, 1/3 r cubed. Evaluate r equals 0 to r equals 2 pi. And then we have our cosine theta d theta. Okay, so plug in 0, you get 0. Plug in 2 pi, well, you're going to get 8 pi cubed. We already have a pi cubed. So we really have what's left. Well, if we cancel the pi cubes, we'll have 8/3. And then we have cosine theta and d theta. Okay, well, great. Integral of cosine is sine, positive sine. Evaluate from theta equals 0 to theta equals pi over 2. And when you plug in pi over 2, you get 1. When you plug in 0, you get 0. And so our answer is 8/3. Good. Good. Now, one thing that's kind of reasonable to ask is, does this make sense? All right. So how do we do this? Well, one way we can do this is to say, well, where is 8/3? Well, it's a little bit less than 3. It's 2.6666. Well, excuse me, 2.6666, right? Engineers, 4 digits of precision. And okay, so what is 2 pi? 2 pi, well, pi is 3.1415. So 2 pi, well, that's 6.2 2, 8, 3, something. Okay. So that says, where does 2.66 lie in relationship to 2 pi? It's a little bit less than half, so it's roughly right here. Now, does this make sense? And, well, if you think about it, if it were outside, that would be terrible. For negative, that'd be really bizarre. So 8/3 isn't too bad. There's another way to phrase this whole problem, and which is to say, what is the x-coordinate for the center of mass given uniform density? So it's really a center of mass problem in disguise when they phrase it this way. And you think of it, well, okay, so center of mass, it doesn't mean it's half the mass is one side, half the mass is on the other side, but roughly it should balance. And you can see that, well, while there's more distance on this side, the circle comes down. So yeah, that seems like a reasonable balance point. So okay, so good. There we go. That wasn't so bad, right? Nah, we got this. Yeah, good times. Rewrite the integral, and it's a triple integral. And what are we doing? We're going to go 0 to 2, 0 to 4 minus 2y, 0 to 3 minus 3/4 x minus 3/2 y, dz dx dy. And when I say, wait, where's the function? 1. So the function is 1. So we're not actually integrating this. We're just changing the order of integration. So it's okay that they don't really write down a function. It's just 1. All right, life is good. So a time for us to say, can we understand 3 dimensions? And these kinds of problems are some of the most challenging because you have to sort of say, what's going on? So let's talk about what's going on. So we'll start with our outer layer and work in. So we're told that y is going from 0 to 2. That's our outer layer. Our middle layer tells us that x is going from 0 up to 4 minus 2y. And our innermost layer says 0 is less than or equal to z is less than or equal to 3 minus 3/4 x minus 3/2 y. All right, so pay attention, right? So we know the outer layer is the y, and it's 0, 2. Y, 0, 2. Inner is x, and it goes 0, 4 minus 2y. And then the last layer is z, and it goes 0 to 3 minus 3/4 x minus 3/2 y. All right, so these are inequalities, and these collections of inequalities are describing our region. And what we're trying to do is say, hey, what does this region look like? Now, it's not the easiest to understand right away, so let's build up our understanding, and that's perfectly fine. We say, well, let's start simple. Let's start with just the y. And we say, okay, y is going from 0 to 2, and we kind of understand that. That says if we were, an interval, it's 0 to 2, and there's our what's happening. Okay, all right, great. What if we now combine y and x? So these were going between 2 numbers. Now we're going between 2 curves, and whereas this is 1-dimensional, this will be 2-dimensional. So we're sort of working our way up in dimensions. Good news, just I don't want to make anybody nervous, we're not going to do 4 dimensions because unfortunately that requires highly specialized paper, and the math department can barely afford the paper already. So we're going to stop at dimension 3. Okay, good. But what's happening here? Well, we have our curves, and we're in 2 dimensions. We already are told that we have y going from 0 to 2, so we have 0 and 2. And so now we want to think about the curves. So there's really 2 curves here. There's a curve x equals 0. Now that's the axis. There's the curve x equals 4 minus 2y. Now we know that's a straight line. We can solve for y, and we probably will at some point. But for now, let's actually just say, oh, if x equals 4 minus 2y, well, if I plug in y equals 0, I'm at x equals 4. So that says I'm going to move from 0 all over to 4. And if we put in y equals 2, we get x equals 0. And we say, okay, that means it's a line that travels through those points. And what's happening is we're going from y equals 0 to y equals 2, and x goes from 0 over to 4 minus 2y. So it's a triangle. So there we go. There's our region if we only look at the two outermost layers. But now we say, well, yeah, but there's one more layer. Oh, yes, there is, and indeed, it's probably the most interesting layer. So, okay, now we're ready to go into the third dimension. And when we go into the third dimension, we're going to be looking at not curves, but surfaces. Okay, so let's first off, before I sketch anything, I'll mention the surfaces. Bottom surface, z equals 0. The top surface, that's z equals 3 minus 3/4 x minus 3/2 y. All right. So, it's going to be a little bit sketchy here, but that's okay. Now, just as we said, oh, I can mark 0 to 2, then think about how that interacts with the curves. We'll do the same thing here. We'll say, let's translate this into our picture. So how do we do that? Well, let's mark things. And we say, okay, so we know x, it's going from 0 to 4. So we're going to mark here a 4. Y goes 0 to 2. So we'll mark here a 2. And then our region is this triangle. So this is the triangle. Now, where are we going between? Well, the good news is we're going from z equals 0. That's the xy plane. And so we say, aha, great. We're going to go straight up from here to something. So z equals 0, xy plane. So this, we need to understand that. And it's not the worst thing to understand. If you look at it, it looks a lot like a plane. And that's because it's a plane. But which plane? And how do we plot it? Well, let's rewrite it a bit. And so we're going to think about how can we go about rewriting this. And I'm going to move the variables over to the one side and just clear out the denominators. And because I don't like fractions. Me and fractions, we've had a bad history. It's, I mean, we tolerate each other, but I would say we've given each other headaches. So if I move this to the other side, we get 3/4 x plus 3/2 y plus z equals 3. Multiply through by 4. 3x plus 6y plus 4z equals 12. Now, how do you plot this? That's not such an easy question. So one thing to remember is if you know 3 points, you know the plane. So let's do 3 points. And the easiest 3 points is where do you hit the axes at? So if I want to know where I hit the x-axis, well, that says cover up the y and the z terms. And then you get, well, 3x equals 12. That means we're going to hit the x-axis at 4. Ooh, well, that's rather convenient. Where do we hit the y-axis? Well, that says 6y equals 12. Y equals 2. Where do we hit the z-axis? 4z equals 12, or z equals 3. So the plane is this plane. And now what's happening is we're going from a point down here up until we hit this plane. And we're doing it for every point in this triangle. So we're going and we're going to form this shape. So what's our shape? And we see our shape is a tetrahedron. All right, good. And all right, So let's see. We'll draw it one more time, because now that we understand our shape, we got to start thinking about setting ourselves up for success for describing it. So x, y, z, and we're going to mark our points here. We have 4, 3, 2, and we have the origin. And then what is our region? It is the one that connects these points together. So we have, that's one face in the xz plane. Here's another face in the yz plane. Here's a face in the xy plane. And, well, we'll use one more. And there's a sort of slanted face at an angle. Okay, so we're ready to talk about setting up our new bounds. Okay, so let's think about what's going on. We're going to do an integral, 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 and the order is dx, dy, dz. All right, so let's think about it. Now you can go inside out, sorry, outside in, inside out. It doesn't really matter too much. It's just whatever helps you think conceptually. Now, for me, I just want to understand what's happening. Now, previously, if we think about what's going on, is when we're doing our inner layer, we're going dz. So here, when we set up our bounds, we're going from top down to the bottom. Now, we're going to have dx be our inner layer. So we're going to be moving, from this back up to the front. So it's useful to know what's your back surface, what's your front surface. And we say, okay, well, the back, well, that's going to be this surface, that's the YZ plane. So we say, this is our backside, that's the YZ plane, and that corresponds to x equals 0. So that we're starting here, then we're going to move forward until we hit the slanted face. So we're going to go from our x equals 0 up to this plane. But we need to have it in terms of x. Because remember how our bound, it's like here, it's z equals 0. Z equals 3 minus 3 fourths, x minus 3 has y. So we need x. X equals. So we're going to rewrite it in terms of x. So 3x equals 12 minus 6y minus 4z. Or x equals 4 minus 2y minus 4/3 z. That's where we're going to. That's the front face. So we're going to go from 0 to 4 minus 2y minus 4/3 z. Good, good. All right, now that handles our inner layer. For our next layer, it says, hey, since we've handled x, let's sort of shift our focus. So we're going to try to like turn. And if you will, it's like, well, we're taking currently our x looks like this, and we're going to move it so it looks like that. So in other words, we're looking down the x-axis. And if we look down the x-axis, what do we see? Well, we're not going to see x. And if you like, you can think that the x-axis has become just the point at the origin. So what do we see? Well, we see the YZ plane. And we say, oh, well, in the YZ plane, what we see for our shape is we see it's a triangle. That looks something like this. And we say, now we have a pretty good idea of what to do. We can figure things out. Now we can label and get our slope here. So if I label this y as a function of z, or z is a function of y, well, let's say z is a function of y to begin with. So z equals 3, then our slope is down 3 over 2 minus 3/2 y. But, of course, we can move stuff around and also solve for y. You can say, look, this is the same as y is equal to 2, because I move this, I move that, so 2 minus 2/3 z. Now, where are we going from? Well, notice we're going, we're doing our outer layers and then it's dy. So we're slicing this way. Okay, that's dy dz. So where does y go from? Well, y goes from the left-hand side, which is y equals 0, to the right-hand side, which is, again, we need y equals 2 minus 2/3 z. And then say, okay, but where does z go from? Z goes from 0 to 3. And now what? We're done. That's it. That's our new bounds. So we go 0 to 3, 0 to 2 minus 2/3 z, 0 to 4 minus 2y minus 4/3 z, dx, dy, dz. All right. This is something that takes practice. It's going to take time, but build up. Just think about what's going on. You say, okay, we can handle 2 dimensions. Great. Wonderful place to start, handling 2 dimensions. And then your innermost layer is surfaces. And think about, what do your surfaces look like? They will be very simple surfaces, things that you've seen, or surfaces which have a missing variable. And those are very easy to draw, just like, oh, draw one and then copy back and forth. We'll probably see some examples later on. But keep at it. With practice, you'll start to say, okay, I can build up my shape. I understand how I'm currently slicing. I can think about how I'm changing how I slice, and then I can start getting my new bounds. It's all about describing. We want to know, can you describe this shape? And with practice, you can. This is a learnable skill. You can do it. You can do it. Find the moment of inertia about the origin, I0, of a thin plate of constant density, we'll make the density 7, in the first quadrant, bounded by the coordinate axes and the line y equals 2 minus x. All right. Well, where do we begin? So first off, let's talk about what inertia is. So when we're talking about inertia, we're really talking about the following. So the inertia is you take a distance quantity squared times a mass. All right. So that's inertia of a little tiny thing. So if you know a little tiny piece and how much mass it has, how far away it is from your object. So we always talk about inertia with respect to something or about something. That's the idea. Now, where does integration come in? Well, integration comes in by saying, well, now if you have a big object, break it into pieces, add them up. And we say, okay, well, great. And break into smaller and smaller pieces, and instead of a sum, you get an integral. And well, that's a 2-dimensional integral. So we'll mark it here. It depends on the problem, but for us it's 2 dimensions. We have our distance quantity squared. And now we say, okay, how do you find mass? Well, mass is our density times our area. And our area, we've broken up into little tiny pieces. That's dA. So density dA. And say, all right, good. So this is, we'll make a note here, mass. All right, now we're after I0. And so if we think about it, we say, okay, we have our little tiny piece. What's our distance to the origin? So if we have a point here, let's say this is at xy, our distance would be the square root of x squared plus y squared. And if we do distance squared, that becomes x squared plus y squared. All right, good. Now, on a side note, some people, like me, I like to call this not I0, I like to think of this as IZ, because I like to think of it as there's this unseen z-axis coming out. All right, well, so what do we do? Well, we're almost there, right? We say, okay, this is our integral over our region of x squared plus y squared, and then our density is 7 and dA. So that's what we need to compute. So we say, okay, cool. And we're almost done, right? Well, no. We actually have to carry out the integral. So let's start by setting up our bounds. So let's sketch our region. We know we're in the first quadrant. So x and y are both greater than or equal to 0. That's what that means. We have this line y equals 2 minus x, which will intersect here, and then has a slope of 1. So it'll go down to there. And so it's a triangle. And so we say, all right, our region is this triangle in the plane. And, well, we get the following. We say, okay, this is y equals 2 minus x. And, okay, well, as they say, and brace yourself. We'll do this the long way. Then we'll come back and talk about other ways to do this. And, all right. Well, so what's our integral? It's integral of 0 to 2. So I'm going to do dy dx. So I'm thinking about slicing this way. 0 to 2 for x. And I'll put that 7x squared plus y squared dy dx. Oops, and I need my innermost layer. Okay, let me start writing that again. Equals integral 0 to 2 integral 7x squared plus y squared dy dx. And now, where does y go from? Y goes from 0 up to 2 minus x. Okay, well, let's integrate. So what will this be? This will be the integral 0 to 2. And then we have the 7. Well, that's going to come along for the right. I'll put a 7 out in front for now. 7, x squared with respect to y, x squared y. Y squared with respect to y, 1/3 y cubed. And then we're going to evaluate that from y equals 0 to y equals 2 minus x. All right, well, that's 7 integral 0 to 2 of x squared times 2 minus x plus 1/3 2 minus x cubed dx. And, all right, well, now, what can we do? What we can do is we can expand that. I would discourage that because if you do, and it can work, you can expand it out, but then you have to say, well, what's the cube? And then you're going to have a lot of terms to keep track of. That's going to be messy. And essentially say, well, 2 minus x cubed is basically like u cubed. It's like, yeah, that one you can basically do without much work. Now the first integral, well, that one, it is better to distribute because this is a x, this is a 2 minus x. They're not mixing well. So we'll write as 2x squared minus x cubed. And again, we'll do this as 1/3 2 minus x cubed. All right, good, good. And now what? Well, we can say that this is equal to, we still have our 7 integral, oh, no, we're not doing the integral. We actually are going to carry out the integral. Integral of x squared 2/3 x cubed. Integral of x cubed, 1/4 x to the 4th. Integral of 2 minus x cubed, there's already 1/3, so it's going to be 1/3. We're going to add 1, so that's going to be 4. Bring it down 1/12. And then we're going to have 2 minus x to the 4th. And then we have to account for the fact that it's not x. It's 2 minus x. How do you do that? Well, it's a linear expression, and so you divide by the coefficient of x, which means divide by -1, which is the same thing as multiply by -1. And then evaluate x equals 0 to x equals 2 All right. Well, that's what? Well, when you plug in 2, you get 7 times 2/3 times 2 cubed. 2 cubed is 8, so that'll become 16/3. Then you have 2 to the 4th is 16 over 4, minus 4. Then you plug in 2, you get 0. Gone. Nice. All right, so 16 over 3, subtract 4, subtract, plug in 0. 0, 0, not 0. So it's going to be a minus 1/12, right? Minus 1/12, and then times 2 to the 4th, which is 16. All right, well, what is this? 12 goes into 16, and that would be 4, right? They both have a common factor of 4, and so this is the same as 4/3. Yes? Good? Okay, and now we have 16/3 plus 4/3. Well, that makes 20 over 3. 16 plus 4 is 20. Subtract 4, subtract 12 over 3, and that gives us 8 over 3. And then if you multiply, that leaves us with 56 over 3. All right, good, good. Actually, that was a little bit easier than I thought, because I was nervous. Because initially when I saw this, I was like, you have to integrate y cubed. That's terrible. Because that y cubed becomes 2 minus x cubed, and you expand. Don't expand if you don't have to. Sometimes you'd have to, but not here. And then just carefully work it out. Now, what could you have done? Well, it turns out this problem has lots of symmetry. And you could have said, well, if I just integrate with respect to x squared, that's the same as if I integrate with respect to y squared. So if you just do one of the two integrals and double, then you'd be okay. But you're relying on symmetry. Not everything has symmetry, so that won't always work. Another thing that you can think about is to say, well, if I integrate with respect to x, it's not too bad when I do the x squared, but it is bad when I integrate with respect to x if I do the y squared. So what you can do is you can say, oh, let me break this into 2 integrals, and for each integral, I'll do a different order of integration. But on this one, I think it's okay to just go ahead and follow your nose and see where it leads you. So, all right, good. Whew. Problem done. Good, good. Integrate the function log of x squared plus y squared to the 5/2 over x squared plus y squared over the region R, which has x squared plus y squared less than or equal to 1, less than or equal to 16. Ugh. This looks hopeless, right? Even our region. What is that? It's 2 circles. And if you sketch, say, well, there's one circle of radius 1, and then you go out radius 4, and our region is the one between them. So you could say something fancy like an annulus, and which basically is a circle with a hole. But okay, or you could be like, oh, it's kind of like a two-dimensional donut, right? Yeah, it's a lot like a two-dimensional donut. Okay, so there's our region, and all right, so how are we going to do this? Well, there's some hints here. There's actually 2 hints, and we're good at picking up on one hint. We're amazing at picking up on 2. Hint number 1, look at our region. Cartesian is terrible, terrible. We'd have to do so many integrals, we'd have square roots, but polar, whoa, in polar, this is amazing. What's our region in polar? Well, we have symmetry all around, so our angle, it goes between 0 and 2 pi. What about our r? Well, r starts at the center. We go out, we begin our region at 1, which is our inner circle, and we end our region at 4. So r is 1 to 4. Now, this region, in terms of the describing of the region, there's a technical term for this in math. We call this nice, which means numbers. We love it when there's simple numbers to describe our region. So, okay, so that's clue number 1. What's clue number 2? Look at your function. What do you see? Lots and lots of x squareds plus y squareds. And x squareds plus y squareds are prime candidates to work in polar, because in polar, x squared plus y squared has a very simple expression. It's r squared. So remember, we have our basic rules. X is r cosine theta, y is r sine theta, x squared plus y squared equals r squared. Okay, so here we go. So we want to integrate over our region our function dA. Now, we're going to update all our pieces. So we're going to describe our region in terms of polar, we're going to describe our function in terms of polar, and we're going to describe our dA in terms of polar. Let's start by our function. So everywhere you see x squared plus y squared, put r squared. So notice you get r squared to the 5/2. That becomes log of r to the 5th. Right? R squared to the 5/2. Multiply 2 times 5/2. Downstairs, x squared plus y squared becomes r squared. So that's the function. What's the dA? R dr d theta. Okay, so this is our dA. I'm going to make some notes here. So this is our function. This is our dA. And then this part right here is our r. And now that we have our bounds, we can say, our bounds were nice. So theta, 0 to 2 pi, r 1 to 4. Okay, now we're going to use some properties to help simplify this. One thing we can do is use properties of logs. You see this exponent? What can we do with it? Bring it down. It's going down. Down, 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 it's going down. Woohoo! Okay, so, other thing, r upstairs, r downstairs. So, we have, this is integral 0 to 2 pi, integral 1 to 4 of 5 log of r over r dr d theta. Now, this isn't maybe the nicest looking integral. We say, well, it's definitely not one that we have memorized, but that's all right. We start sort of working through our process. Say, well, if it's not one we have memorized, is there some simple algebra or trig? Nope. Is there a good substitution? Well, notice we have a couple pieces. We have log of r and 1 over r. So, well, wait a second. Log r, 1 over r, I've heard something before. Those seem to be connected. The derivative of log r is 1 over r. Idea. So, we have a plan. All right, so for this inner layer, we'll say, well, let's let u equal log of r. du would become 1 over r dr. So, if we update, we haven't done anything to the outer layer. And we're going to have the integral. And for r equals 1, u would be log of 1, 0. For r equals 4, u would be log of 4, which is log of 4. And then we have the 5, and then log of r becomes our u, and 1 over r becomes our du. And that's all, on the inside there's a d theta. But now we're like, that's something we can work with. So this becomes the integral from 0 to 2 pi. We can integrate, we get 5/2 u squared, evaluated from u equals 0 to u equals log of 4, and then d theta. When you plug in 0, you get 0, which is good. Plug in log 4, well, you're going to get 5/2 times log of 4 squared. Which, by the way, this square is outside of the log. It does not come down, so be careful. Make sure your parentheses game is on point. So that too does not come down. Well, we still have our d theta. Now, this is a constant. It's a long, complicated looking constant, but it's still a constant. So we get 5 halves log 4 squared times theta from 0 to 2 pi. Well, plug in 0, you get 0. That's good news. Plug in 2 pi, well, you get 2 pi. So 5 halves log of 4 squared times 2 pi. The 2's cancel, leaving us with, I'll put the pi a little bit closer to the front, 5 pi times log of 4 quantity squared. Not so bad, right? No, not so bad. We can do it. How do we know we can do it? We did it. Yep, that's a good sign that we can do it. So there you go. All right, cool. Rewrite the integral from -2 to 2, integral y squared to 4, integral 0 to 4 minus z, dz, dx, dy, in the order dy, dz, dx. Okay. Now, I'm going to just preface this by saying, take your time and be patient with yourself. And so let's go through and carefully think about the process. So we're going to be changing our integration. So first thing is, let's figure out what our current description is. We're going to get that from our bounds. Once we have those, we're going to say, let's draw a picture. And now that's going to do a little bit of our test of our, can we think geometrically? So we're going to be careful with that. Once we have our picture, then we're going to make sure we label everything really nicely, and then we're going to start figuring out our new bounds. Okay, so let's begin. So getting our existing bounds is actually not too bad, because the existing bounds or existing description is encoded into the integral. So notice here our outer layer is a y, and so that says we're going from y equals -2 to y equals 2. Our inner layer is, our middle layer, not our inner layer. Our middle layer is an x, so x equals 2 to x equals 4. And then our true inner layer, or innermost layer, if you will, z equals 0 to z equals 4 minus x. Okay, so it's just doing our classic pair things up. So we write this down. We know that -2 less than or equal to y less than or equal to +2. We have that y squared less than or equal to x less than or equal to 4. And we have that 0 less than or equal to z less than or equal to 4 minus x. All right, so now we're going to just start describing things. Well, -2 less than or equal to y less than or equal to 2, that's pretty easy to describe. And so let's work on just the two-dimensional part here. So we'll go into our y and x plane, so x and y. And what do we see? Well, we'll start, y goes from -2 to +2. So here's -2, here's +2. So I'm in the x, y. Where does x go from? So because we see x moving depending on y, we're doing our horizontal slices. So we want to think about the curves. So we have two curves. We have x equals 4, x equals y squared. Now x equals 4, that's actually a pretty straightforward curve to plot, and that would look something like this. X equals 4. Now x equals y squared is like y equals x squared, but we turn it, let's see which way, on its side. No. Well, one of these works. All right, so we're going to have here, and it just comes here, and very conveniently, almost as if the person who wrote this problem planned it, is if you plug in y equals -2, then you'll see that -2 squared is the same as 4. So they actually do intersect at -2. Similarly, if you plug in 2, 2 squared is 4. It's like I said, it's like it was planned, like it was meant to be. So x equals y squared. Okay, so our region, if we think about our slicing, is we're slicing from y squared over 2, 4. So that's our shape. So it's the piece of a parabola. All right. Now that's our two-dimensional picture, and that's already feels like we've had a good workout. But the fun has just begun. Now we're going to go up to our three-dimensional picture. Okay. Ooh, this is going to be fun. And we have to think about what's going on. So we see that we're going to have two surfaces. Z equals 0. Now this is not a number, it's not a line, it's a surface. So this is equal to what? That's the xy plane. Okay, good, we'll keep that in mind. And now we have this other thing, which is z equals 4 minus x. Now this is a plane, but it's not xy. Yeah, there's a little bit involved. So let's see what we're dealing with. So we are sketching here, and let's mark what's going on. Okay, so I'm going to first sketch this region here, and I'm just going to be very, very cautious and not try to make it too ornate. We know y is going from -2 to +2, and then we have this x equals y squared, and so we have this. So here, and there we go. So that this shape right here, this is our floor, and the good news is the xy plane is indeed part of it. So this is that. Okay, good. Now, we know the xy plane. That's the floor. And so the bottom looks like the bottom. So the shaded part is indeed the bottom. And okay, so we can just mark sort of the back side. Here is we have z equals 0, the xy plane. And now what's the top? Okay, so what does z equals 4 minus x look like? Now, if you think about it for a second, I'm going to sketch a picture over here. So if we just had x and z equals 4 minus x would say, well, you intersect here at 4, you intersect here at 4, and you have a line. That's what it would look like if we were just two-dimensional. But we're not just two-dimensional, we're three-dimensional. So how do we get that extra little oomph in? So what you can think about is, says, well, hey, you have this line, but you always have the same line. So you're going to have this copied left and right. So essentially it's a slanted surface. It's like you're leaning a board against a wall. And so we say, oh, okay, now what's going to happen to this? Well, if you think about it, here we say this is intersecting up here at z equals 4. Now this part down here, that's at x equals 4. And then we have this board slanted up. So what's the shape is going to be is it's going to come up, and we're just going from the parabola, right? We always have to be above the parabola, up. Okay? All right. This is, pictures always get a little bit more complicated to see. If we sort of turn it a little bit, so let's say we rotate it, another way to see what's going on is we have this sort of shape going on. So it's sort of a wedge, if you will, where it has this parabola shape and it's coming in. So there's another view of our picture. All right, so our solid is this wedge-shaped thing. Okay, so with this in mind, let's try to see if we can't sketch it one more time, but we'll do it without so much clutter. It's nice to be able to draw things without too much clutter. And so we're going to have here 4. And we have a segment here. And we're coming up. I'm going to use some different colors here. So we have our top surface here, which looks like the parabola lifted up. We have the parabola underneath, and I'm going to draw a dotted line, not because it's not there, but just sort of to emphasize. And then we have the sides, and the sides, so there's 3 surfaces that are bounding here. We have the z equals 0, we have this top surface, z equals 4 minus x, and then we have this parabola that's just going straight up from the xy plane to there. Now what's that surface? It's the following, namely, it's this x equals y squared. Okay, so our 3 surfaces are as follows. We have the sides, x equals y squared. The top, z equals 4 minus x. The bottom is, sorry, not x, it's z. Z equals 0. All right. Okay. So we're at step 2. We figured out our bounds, and we worked to get a picture. So now we got to do the rest of it. Well, thankfully we still have some paper left. Okay, so what's our order going to end up being? Well, we look and we say, what's our innermost layer? And it says dy. And we're like, oh. Of all the choices that they could have made. Okay, so you might be saying, what? Why is that? Why are you chuckling? Well, it actually isn't too bad. It could have been a dx on the inside. But, okay, so if the inside had been dz, oh, that would have been such an easy one. If the inner layer doesn't change, then it makes everything much simpler. So you have to think about what direction you're going in. So see how we're dy? So let's actually come back here. See how the innermost layer is dz? What that means is you're really going in the z direction. So you're thinking of going up, down, parallel to the z. So now when you're doing dy, we want to move in the y direction. Okay. Oh, I was right. No. dx would have been nice. The dy. So we're moving left, right. So we're moving from this over to that. So we're moving between the 2 sides. Now, that means we have to think about, wait, is that 1 surface or is it 2? Well, it's 1 if we describe x in terms of y. It's 2 if it's y in terms of x. So on this side, well, because you can solve for y, we get y equals square root of x. On this other side, y equals minus square root of x. Okay, so we're ready to get going. We're going to have an integral, give ourselves spaces, and we have dy, dz, dx. Okay, since it's y, we're going back and forth between the sides. So we're going from low to high. We always go low to high. So lowest value is minus root x, highest value is plus root x. So that's what y does. It's going between surfaces. So we're thinking about what are the surfaces. Now, what comes next? Well, we've got the surfaces done, and we say, well, let's look down the y-axis. So we're going to take this, and we're going to pivot to we're looking straight down the y. So y right now is doing this, and we want to turn, so we look straight down the y. And if we look straight down the y, what do we see? We see the xz plane. In other words, we're seeing this triangle. Oh, cool. Now with the triangle, that's actually pretty convenient for us because we know how to describe this. And so what is z? Well, where does z go from? And here we're slicing up and down. So z goes from 0 up to this curve. And this is the curve 4 minus x. So it goes 0 up to 4 minus x. Where does x go from? X goes 0 to 4. All right, so what happened? Sometimes you're like, wait so long, and then all of a sudden, like, wow, answer pops out. Like, wait, what happened here? So this portion right here, this is like find the two surfaces we go between. And know the direction you're going. And use your axes to help you. So if you're going in the y direction, you're moving parallel to the y-axis. So you're moving that way. If you were doing x, you're moving this way. If you're doing z, you're going up, down. So here, we're integrating with respect to z, we're going up, down. Here, since with respect to y, it's left to right. All right, so we found those two surfaces. That gives us our inner bounds. So here, the way we find these is we say, okay, look down the axis and do the two-dimensional picture. So when we look down the axis, what did we see? We saw in the xz plane, and I'm just copying it again. So down the axis, that means that here, this point, this is the y-axis now, and your shape from the side, when you look at it from that perspective, it looks like a triangle. And you're not seeing the parabola because you've changed your perspective. Changing your perspective changes the curve. And you say, okay, well now I can describe this two-dimensional region, and you use tools that you're already more familiar with. And then life is good. So there we go. All right, good. Whew, this might be the hardest one on this quiz. Maybe one of the hardest ones in the semester. Or, as a pessimist might say, well, it's the hardest one so far. We still have a few weeks left. Let's find out what the future holds. Find the volume of the solid bounded by the surfaces x squared equals 2z, y plus 2z equals 4, and y equals 0. All right, well, interesting. Let's see what this looks like. In some sense, it feels very, very similar to the problem we just did, except there's no integral to start with. They just say, okay, we're giving you surfaces. Well, let's start sketching things. And okay, so we can identify a couple things pretty quickly. So y equals 0, that's an easy surface. That's going to be our xz plane. All right, well that's good. We have the xz plane. Y plus 2z equals 4. That's going to be a, okay, let's think about that. It's also going to be a plane, but okay, let's actually sketch. Let's actually do a sketch here. So y equals 0, xz plane. So So we have our x, y, z. So the xz plane is going to be this part. So here's our xz plane. All right, so that's our y equals 0 now. Of course, that's not the whole plane, but just to sort of give you an idea. Okay, so there's our first bound. Now y plus 2z equals 4. Let's see, what would that look like? Well, notice there's no x. That's actually to our advantage. When there's a variable missing, that says it's kind of like draw the one, two-dimensional thing, like here, one variable less, copy. Okay, so y plus 2z equals 4, and okay, so what would that look like? So think about what would happen in just y and z. So we can find where it intersects. So for example, it would hit at y equals 4, and here it would hit at z equals 2. So it would be this line. And now you just copy that line. So we're running parallel to x, and so we have this, again, it's like a board leaning against the wall. So we have, that's our y plus 2z equals 4. All right. So that brings us now to our last one, x squared equals 2z. Now what does that look like? Well, again, there's no y. And so we say, okay, so what can we do? Well, so we'll sketch it, and we'll do it in the xz plane, and then we'll see what happens here. So we have the following. In the xz plane, so we have, remember here, we have our x, y, z. Then what will happen is it's z equals 1/2 x squared. So it's a parabola opening up. So in the xz plane, we have this upward parabola. And now we're just copying it left and right in the y direction. So it's this trough shape that's being formed here as we move along. So okay, so that's our surface. We have a trough. Okay, so we start thinking about what do these things do? Well, the xz plane, it says like, okay, cut it off, and if we look, there's not going to be a nice bounded piece. So we're going to ignore now the values y less than 0. And then if you say, okay, I'm got to be thinking about how these intersect, how they interact really, and what we'll see is that we have sort of the following. It's a piece of the trough that's been cut off. So I say, okay, all right. So what's going on? Well, I'm pausing a lot, and it's one of those things where it's like, it's hard to sometimes put things into words. It's, of course, the famous saying, a picture is worth 1,000 words. And but sometimes it takes more than 1,000 words to really describe things well. So we're slicing into this trough. So we're going to come, we really care about what's happening here at z equals 2. Now at z equals 2, let's think about what's happening with our x values. If we put z equals 2, we have 2 squared is 4. 2 times 2 is 4. X squared is 4. So that says, oh, you have these values, positive 2, and back behind here is negative 2. And now you have this parabola. Okay, so it's essentially we're intersecting the parabola with the xz plane, but we're capping it at this z equals 2. And now we have this trough moving forward, but we're going to just keep eating into it as we move down. That's what this upper plane here is doing. And so what we get is this sort of, again, a fun little shape. And so by the time we get over here to 4, it's all the way down and it's back up again. And so it's this sort of going lower down in the trough. So yeah. So that's our rough shape. And there we go. Okay. So I've marked here the parabola, but of course you also have your top surface, and your top surface is just this flat plane here. So this is the tongue, is this plane. All right. So, okay, so the top, this is our y plus 2z equals 4. That's here. The back, that's our y equals 0, And then the bottom, that's our x squared equals 2z. Whoops. X squared equals 2z. Okay. Or z equals a half x squared. All right. Good. Good. Whew. Okay. Now, what to do? Well, we have to make a decision in that we're finding our volume. So how do you find volume? Well, the way you find volume is the integral over the solid of 1 dV. It's one of our applications of integration. So given that we have our volume is this integral of 1 over our solid, we have to actually do the integral. It's not just like, oh, theoretically, okay, yeah, great. But we got to put, rubber to the road. How do we do this? What do we do? And, all right, well, we have to decide which order of integration do we want. And in other words, how do we want to move? So maybe a few different images. If we tilt up a little bit more, we'll see that what we have here, we have this sort of tongue on the top, and then we're coming around to the bottom side. So we have these things coming down. Now, when I ask the question, how do we want to integrate, and it comes down to how do you want to cut things up. So do you want to go in the x direction? This would be the x direction. Do we want to move in the y direction? This would be the y direction. Or do we want to move in the z direction? And for that, we want to say, well, what surfaces are easy for us to work with? And there's sort of this mantra, 0 is our friend. So, with that in mind, we look at the picture and say, well, which surfaces are the easiest to describe and think about? And we say, what's really easy is moving here in the y direction, because we're going to move from this back surface up till we hit the plane. So that's what's happening in the y direction. So it's like, oh, let's integrate. So our innermost layer is going to be with respect to y, because that's going to be our easiest surfaces to work with. So our plan, we're going to integrate 1 dy. And now, when we talk about y, we're going from the back, y equals 0, to the front, which is 4 minus 2z. Okay, now we still have more layers to figure out. Okay, so to figure out our next layers, let's look down the y-axis. So we're going to pick this up and look down the y-axis. So we're looking down the y-axis. So pick it up, look down the y-axis. What do you see when you look down the y-axis? Well, what you're going to see is that parabola. So we're in the xz plane, and we see our parabolas here. We have -2, +2, and this top part is z equals 2. This is z equals 1/2 x squared. Now, just to note, the origin, that's, boom, that's our y-axis. We're looking down the y-axis. And so when we look from this direction, our solid, it just says, oh, you're just a parabola. And if you're trying to, again, think about, wait, what does our solid look like? It's very thin at the top, and it becomes thicker at the bottom. So it's, okay. Now, we don't need to worry about what's happening in the y direction. For the next question, how do we want to slice? Do we want to slice up and down, or left to right? Up down looks much more convenient, because these are nice functions. Left right, we end up getting square roots. And as lovely as square roots are, they're not our favorite thing. So if we're slicing up down, well, then that says we're going to go dz dx. Well, where does z go from? It goes from 1/2 x squared up to 2. Where does x go from? From -2 to +2. And now we have the bounds. What's left? We've actually got to do the integral. All right, well, so let's do the integral. One layer at a time. Right, there's no rush. We have plenty of time. So our outer two layers, we haven't done anything. We're integrating the inside with respect to y, which gives us y. And we're going to evaluate y equals 0 to y equals 4 minus 2z. And then we have our outer layers. Okay, so that's integral -2 to +2. Integral 1/2 x squared to 2. Well, plug in 0, you get 0. Plug in 4 minus 2z, you get 4 minus 2z. Okay, great. We can work with that. Well, what's the integral of 4 minus 2z with respect to z? Well, that would be the 4z minus z squared. All right, and evaluate z equals 1/2 x squared to z equals 2. Now, when you plug in 2, what do you get? You get 4 times 2 is 8, minus 2 squared is 4. So you get 4, subtract 4 times 1/2 x squared. Well, 4 times 1/2 x squared, that'll be 2x squared. Subtract 1/2 x squared squared. All right, half squared is a fourth, so that'll be 1/4 x to the 4th. All right, and that's dx. Okay, good. We're getting close. Now, say, can we save ourselves any work? Well, yes. You see how we have just even powers? This is an even function. You see how we're integrating from -2 to +2? So we're integrating in a symmetrical thing about the origin. We can combine these and say, let's cut our work in half. And this is the same as doubling the integral from 0 to 2. And 0 is a friend. So that's good. So then we have our 4 minus 2x squared minus minus makes plus 1/4 x to the 4th. Okay. So we integrate, and we'll also put in the 2. Integral 4 is 4x times 2 makes 8x. Integral of 2x squared, well, that'll be 2/3 x cubed. Don't forget this other 2. So that becomes 4/3 x cubed. Integral of 2 times the 4th is 1/2. Integral of x to the 4th is x to the 5th. So put those together, because you're going to have to divide by 5. You'll end up with 1/10 x to the 5th. Okay, and then we're going to evaluate 0 to 2. Now, we plug in 0, you get 0. Nice! So we just have to plug in 2. And the good news is we're almost done. And I say that's good news because, 1, we've been doing this for a while, but 2, we're running out of space. So, okay, we're going to make it. We're going to make it. All right, so what do we have? We have 8 times 2, 16. 2 cubed is 8. So minus 4 times 8 is 32. Divide by 3. 2 to the 5th is 32 over 10. Now, 10 has a factor of 2. So we can actually do a little bit of cancellation and say this is plus 16 over 5. Well, if we were going to combine these together, because why not? What's our common denominator? 15. 15 times 16 is correct, 240. I knew you were going to get that one. Everybody knows that. 240 over 15. Subtract. Here, multiply by 5. 160 over 15. And here, multiply by 3. 48 over 15. And if we do this, well, that's like 288. subtract 160, and 288 subtract 160, well, I'm going to do this in 2 steps, and that would be 128. 128 over 15. Well, 128 is like a power of 2, so no common factors to cancel. So there we go. We did it. 128 over 15. Good. And other good news. That's a positive number. If we'd gone a negative number for a volume, what would that mean? It would mean that mistakes were made, and we should check our work. If we got 0 as an answer, mistakes were probably made, and we would go and check our work. And but we got 128 over 15. I don't know exactly what that is. It's what, 8 point something, I think? A little over 8, about 8.5. Okay, 8.5. That seems a reasonable answer. And good. Whew. All right. I said the last one was hard. This one is probably just about as hard. Oh, we need a cool down problem. I hope we have some cool down problems coming up. But again, take your time. Practice. Look at old problems. Build up your geometrical intuition. What are the pictures? What are your sides? What are your surfaces? You know, how should you pick order of integration? Keep it simple. Keep it simple. Remember, we love ourselves. And because we love ourselves, we try to make it nice to ourselves. All right. Good. Consider a thin plate covering the planar region satisfying x greater than or equal to 0, y greater than or equal to 0, and x plus y less than or equal to 1. All right, let's do a quick sketch. X, y both being greater than or equal to 0 means first quadrant. So we say, okay, so we're in the first quadrant. Now x plus y equals 1. That's the line y equals 1 minus x. So we have 1 and 1. And so we have our line, y equals 1 minus x. And so our region is a triangle. All right, cool, beautiful. Sketching in our triangle. Okay, so there we go. Now, if the density of the plate is given by, density is 10y plus alpha. Find the value of alpha so that the inertia with respect to y is 3. Now, let's think about what's going on here. It says our density depends on the y. So at the bottom, we get a density of just alpha, since y equals 0. And as you move up, you get all the way up to alpha plus 10. And then we want to find the value of alpha so that I sub y equals 3. So what is I sub y? Now there's sort of 2 clues here. First big clue is there's a letter I. So I means inertia. So it's inertia with respect to something. What? So that's where the subscript comes in. I sub y. So it's inertia with respect to the y-axis. So that's the y. Okay, so now we know what we're trying to find. What is inertia? So let's do a quick recall. So the way we do inertia is you think about taking the following. You're going to take a little tiny piece. Here's my little tiny piece. And now the inertia of that piece is you're adding up the distance squared. So sometimes inertia is called the second moment. So that's the second referring to that 2 times your mass. Now that's just, of course, that little piece. You have to add them all up. And how do we do it? Well, of course, we think of littler and littler pieces, so it becomes the integral over our region of our distance squared times mass. And the way we do mass is we say, well, let's find the density of that region times the area of that region. So there's our generic formula. Now, question, what is our distance? So that's where we have to pay attention with respect to what? Well, we're with respect to the y-axis. So if I want to go to the y-axis, that means my distance is this length here. So the distance is what? It's not y, it's x. So x is how far over you are from the y-axis. So in our case here, this is x. What's our density? It's 10y plus alpha. And so we're saying, cool, we have our pieces in place. So in particular, we know that 3, that's equal to our inertia with respect to y, which is an integral of x squared times 10y plus alpha d something. So iterated integral. How do we integrate? Well, we can choose, right? And it's not going to be too bad. It's polynomial. And I would say let's do our typical slice up and down. And that means integrating dy dx. So where does x go between? 0 to 1. Where does y go between? 0 up to 1 minus x. All right, so we have it, the stage is set. The cast is ready to go. Now we just have to carry out the performance, do the integral. So we're just going to be patient. We're integrating first with respect to y, so this x squared is acting like a constant. So we have integral 0 to 1, and then we have the x squared is a constant, 10y with respect to y will become 5y squared, right? Add 1, divide by 2, plus alpha with respect to y is alpha y. Alpha is a constant, we just don't know what it is. Evaluate from y equals 0 to y equals 1 minus x. Well, okay, that's going to become 0 to 1 of x squared times 5, 1 minus x squared, plus alpha times 1 minus x. And when you plug in 0, you get 0. 0. It's a friend. We like 0. Okay, dx. Now let's clean this up a little bit. And unfortunately, we do have to clean that up. I shouldn't say unfortunately. It's like, oh, we get to, right? In order for us to really do the next thing, we got to expand everything. So 1 minus x quantity squared. That would give us 1 minus 2x plus x squared. Now, let's multiply through. We have the x squared plus the 5 coming in. So this would be 5x squared. Right, that's x squared times 5 times 1 minus 10x cubed, right? X squared times 5 times 2x, and then plus 5x to the 4th, right? X squared times 5 times x squared. Then we also have the x squared coming into the alpha, so alpha x squared, and then we have minus alpha x cubed, right? X squared times alpha times x. All right, that's really what we have there on the inside. Okay, so this is equal to integral 0 to 1. I'm just going to write this down again, 5x squared minus 10x cubed plus 5x to the 4th plus alpha x squared minus alpha x cubed dx, which is, now we can integrate term by term. 5 over 3 x cubed, all right, good, minus 10 over 4 x to the 4th plus 5 over 5 x to the 5th plus alpha over 3 x to the 3 minus alpha over 4 x to the 4. And evaluate that from 0 to 1. Good. Now, good news. 0 is again a wonderful friend, because when you plug in x to the, x is 0 and 0 to the power, you get 0. 1 is a good friend too. 1 to any power is 1. So what's left? it's our coefficients. So we have 5 over 3 minus 10 over 4. Actually, that's instead of 10 over 4, that's right, that's 5 over 2. And 5 over 5 is 1. And then you have alpha over 3 minus alpha over 4. Okay, well, we're almost there. Let's clean it up. So let's say first with our constant terms, what do we have? We have an over 3 and over 2. So let's do this over 6, right? So double. So we'd have 10 over 6 minus, here we'd have 15 over 6. And then we'd have plus 6 over 6, right? So that allows us to add those together. And then we have here 3 and 4, common denominator is 12. So plus 4 alpha over 12 minus 3 alpha over 12. Well, 10 plus 6, 16 minus 15. That gets us to 1 over 6. Subtract. Sorry, actually not subtract. It's going to be added, right? 4 alpha minus 3 alpha. Add alpha over 12. But remember, working your way back, that equals 3. Okay, so we now have the following. We can say, aha, 1 over 6 plus alpha over 12 equals 3. Multiply to get rid of your fraction, so we're going to multiply everything by 12. 1 over 6 times 12 gets us to 2. Alpha over 12 times 12 gets us to alpha. And 12 times 3 is 36. So 2 plus alpha equals 36. And so that tells us that alpha equals 34, which is 36 subtract 2. Yes, that's it. We did it. Woohoo! Now I might think like, that's a huge number. It's not too surprising because there's a fair amount of inertia. And this is a very tiny region. So to build up a large amount of inertia, given that distance squared is going to be a small number, you kind of have to have a lot. So it's not too surprising it's a big number. If it had been a negative number, panic should set in. Because if alpha were negative, that would say that along the bottom, where y equals 0, your density is alpha, negative density. What? That doesn't make sense. That means something went wrong. But for 34, I think we're doing great. I think we're doing wonderful. Evaluate double integral over a region y over x squared plus y squared cubed dA, where the region R is given by all x and y, where both x and y are positive, and x squared plus y squared is greater than or equal to 4. All right. Now, can we just pause and just say, we're very suspicious about this integral, given that we see x squared plus y squared showing up in our bounds, x squared plus y squared showing up in our integral. So much x squared plus y squared, this is making us think polar. So this is almost surely going to be a polar integral. So that's going to be our mindset. Let's actually sketch our region. Well, we're in the first quadrant, and then we have this boundary x squared plus y squared greater than or equal to 4. What does that mean? Well, if you think of x squared plus y squared equals 4, that's a circle of radius 2. So you say, okay, so we have our circle radius 2. And when are we greater than or equal to 4? So it's not this piece of the circle, it's everything else. So there's a lot of everything. So it's we keep going and going and going. So we'd run out of highlighter if we had to highlight the whole thing. So it's a huge, unbounded region. Ooh, well, this might make things interesting. Well, okay, let's see what happens. All right, we already have the mindset polar. So we say, okay, how do we describe this in polar? Well, in terms of the angles, we start at this angle, which is 0, and we stop at pi over 2. So it's from 0 to pi over 2. All right, so those are our angle bounds. All right, and then where does r go from? Well, if you start at the origin and you start going out, you begin at 2, and then you keep going and going and going and keep going. So theta goes from 0 to pi over 2, and r goes from 2 to infinity, unbounded. All right, well, that's actually not a bad integral when it comes to polar coordinates. So let's look at our integral. So we're trying to find integral over our region of y, x squared plus y squared cubed dA. So this is going to become the integral, and let's do it piece by piece. So we have a few pieces. First off, we have our function. So what is that going to become? Well, we just write everything in terms of polar. So we remember, oh, x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. So y becomes r sine theta. X squared plus y squared becomes r squared, and then that's going to be cubed. Now that's the function. We also have the dA. The dA for polar becomes r dr d theta. Now, the last thing we have to deal with is our bounds. That's our region R. So we're doing r dr d theta, so theta goes from 0 to pi over 2, and r goes from 2 to infinity. And there we go. Okay, so that's the integral. Well, let's clean all this up. And so what do we have here? Well, all right, so we have integral 0 to pi over 2, integral 2 to infinity. We have r and r upstairs, that's r squared. We have r to the 6 downstairs. So if we put that all together, we have r to the negative 4 power. And then we have sine of theta dr d theta. So this r to the negative 4 is just keeping track of all the r's together. Okay, well, let's integrate. Now, when we do r to the negative 4, we add 1, divide by that. So we still have the outer layer. Then we're going to have r to the negative 3 times a negative 1/3 in front. So that's dividing by negative 3. And sine of theta, evaluate that from 2 to infinity. Now, when you plug in infinity, when we say plug in, what we really mean is what's happening as we go to infinity. So as we get big, r to the negative 3 gets small. So that means that when we plug in infinity, we're going to get 0. Subtract. Plug in 2. So we're going to have our negative 1/3. 2 to the negative 3 is 1 over 8. And then we have our sine theta. And of course, that's all d theta. All right, so minus, that's the plus. So that's really 1 over 24. And then we integrate sine. Integral of sine, negative cosine. So this is going to be minus 1 over 24 cosine theta. Evaluate from theta equals 0 to theta equals pi over 2. Cosine of pi over 2 is 0. Okay. So it's 0, subtract. Cosine of 0 is 1. Oh, okay, so that makes a minus 1. With that minus, leaves us with a positive number, namely the number 1 over 24. And that's our integral. And there we go. All right, so a nice cool down problem from this set, which this was quite a workout. There are a lot of problems here, and this takes time because this is really the time in the class when we're stretching ourselves geometrically, and that can be challenging. So make sure you're doing the practice, putting in the work, and developing your geometrical intuition. So we want you to be wonderful. We want you to be great because you have that in you. You can do this. Keep at it. Keep at it. All right. Hope to see you again. Bye.